Welcome to Brain Vision.
Okay, in this question, we have this bar with sliders at point B and A here. They're moving along tracks that are in these directions that I'm going to highlight in red here. This bar of length L is a fixed length, and this bar will move, or these objects will move in given slots here, one of them at this angle of 40 degrees with the horizontal, one of them horizontally. And we want to know what the angular velocity of the bar will be in terms of the displacement. So to do that, we'll have to work out a little bit of geometry first. So first, we're going to use the law of sines to compare that horizontal position xa over the sine of theta. We'll have to equal that length L over the sine of 40 degrees. So next, we can differentiate, we can solve for xa, and then we can differentiate with respect to time to get the velocity of A. So the velocity of A will equal L is not changing, so that's just a constant. I'm going to pull that out of our derivative here. So we have the derivative with respect to time, sine of theta d theta. Not a d theta there yet. Just a sine of theta. So when we take that derivative with respect to time, we're left with L over the sine of 40 degrees times the cosine of theta, and then theta dot, which is just the time derivative of theta. So this then gives us the rate at which that angle theta is changing. And that's just that theta dot. So we can solve for that. We'll call that omega here. And that will just equal the velocity of that bar, or velocity A, times the sine of 40 degrees divided by L times the cosine of theta. However, we're not done yet. We still need to find the value of the cosine of theta. So we can do a few things to get there. First, we know that the cosine of theta will equal the square root of 1 minus sine squared of theta. And then we can substitute in for sine of theta the sine of 40 degrees times xa over L, which we could find up from our first equation we wrote. So this leaves us with some simplification. A cosine of theta equals 1 over L times the square root of L squared minus, and we'll put the value in for that sine of 40 degrees here just to make it a little cleaner looking, 0.413 xa squared. So this is what our cosine of theta is. We can then plug that into our omega equation. So that leaves us with omega equals again, we'll put the sine of 40 degrees into our calculator, and here we'll get a 0.643, and times the velocity over L times that cosine of theta, which is 1 over L times the square root of our L squared minus 0.413 xa squared. Well, the L times the 1 over L cancels out here, luckily. Sorry, I hit a button there. Let me try to erase that. Okay. There, that's better. And then we need to make sure we are careful here and say what direction this bar will be spinning. Well, the only possible way it could be moving is a counterclockwise direction. If A is moving to the right, then B must be moving down and to the left. So that would be, in general, a counterclockwise direction. So we can write that as counterclockwise, but then we also have some limits on where the position x could be. So that'll be 0 is less than or equal to xa, which is then less than or equal to the maximum possible position, will just be L divided by the sine of 40 degrees, which would occur when this sine of theta is equal to 1.